Learning objectives. In this chapter, the user would learn the following aspects of number theory: greatest common divisors, Euclidean algorithms, Fibonacci numbers, complexity of Euclidean algorithms, congruences and equivalence relations, public key encryption schemes, dividends. The principle of induction. More generally, we may apply the principle of induction whenever the universe of discourse is a set of integers of the form f of k, k plus 1, k plus 2, where k is some fixed integer. Let p of n be a predictive over f of k, k plus 1, k plus 2, etc., where k belongs to z if number 1 p of k and number 2 p of n or p of n plus 1 then or np of n. In this context, the for all n of course means for all n greater than or equal to k. While the principle of induction is very useful technique for proving propositions about the natural numbers, it isn't always necessary. Principle of induction. Why does the principle of induction work? This is essentially the domino effect. Assume you have shown the premises. In other words, you know P of O is true and you know that P of n implies P of n plus 1 for any integer n greater than or equal to 0. Using mathematical induction, steps: number 1, prove the basis step. Number 2, prove the inductive step. Assume P of n for arbitrary n in the universe. This is called the induction hypothesis. Prove P of n plus 1 follows from the previous steps. The first principle of mathematical induction. If a set of positive integers has the property that if it contains the integer k, then it is also contains k plus 1, and if this set contains 1, then it must be the set of all positive integers. More generally, a property concerning the positive integer that is true for n equal to 1 and that is true for the integer n plus 1 whenever it is true for the integer n must be true for all positive integers. We use the well-ordering principle to prove the first principle of mathematical induction. Proof. Let S be the set of positive integers containing the integer 1 and the integer k plus 1 whenever it contains k. Assume also that S is not the set of all positive integers. As a result, there are some integers that are not contained in S, and thus those integers must have a least element alpha by the well-ordering principle. Notice that alpha equal to factorial 1 since 1 belongs to S, but alpha minus 1 belongs to S, and thus using the property of S, alpha belongs to S. Example 1. Use mathematical induction to show that 8n belongs to n. Summation j equal to 1 to n, j equal to n into n plus 1 by 2. First note that summation j equal to 1 to n, j equal to n into n plus 1 by 2. And thus the statement is true for n equal to 1. For the remaining inductive step, suppose that the formula holds for n, that is summation j equal to 1 to n, j equal to n into n plus 1 by 2. We show that summation j equal to 1 to n plus 1, j equal to n into n plus 1 by 2. To complete the proof by induction, indeed, summation j equal to 1 to n plus 1, j equal to summation j equal to 1 to n, j plus n plus 1 equal to n into n plus 1 by 2 plus n plus 1 equal to n plus 1 into n plus 2 by 2. And the result shows. Example 2. Use mathematical induction to prove that n factorial less than or equal to n power n for all positive integers n. Note that 1 factorial equal to 1 less than or equal to 1 power 1 equal to 1. We now present the inductive step. Suppose that n factorial less than or equal to n power n for some n. We prove that n plus 1 factorial less than or equal to n plus 1 into n plus 1. Note that n plus 1 factorial equal to n plus 1 into n factorial less than or equal to n plus 1 into n power n less than n plus 1 into n plus 1 into n equal to n plus n whole power n plus 1. This completes the proof. The second principle of mathematical induction, a set of positive integers that has the property that for every integer k, if it contains all integers 1 through k, then it contains k plus 1, and if it contains 1, then it must be the set of all positive integers. More generally, a property concerning the positive integers that is true for n equal to 1 and that is true for all integers up to n plus 1. Whenever it is true for all integers up to n, must be true for all positive integers. The second principle of induction is also known as the principle of strong induction. Also, the first principle of induction is known as the principle of weak induction. To prove the second principle of induction, we use the first principle of induction. Proof: let T be a set of integers containing 1 and such that for every positive integer k, if it contains 1, 2, etc. k, then it contains k plus 1. Let S be the set of all positive integers k such that all the positive integers less than or equal to k are in T, then 1 is in S, and we also see that k plus 1 is in S, thus S must be the set of all positive integers. Thus, T must be the set of all positive integers since S is a subset of T. Example 1. Prove every integer n greater than or equal to 2 can be expressed as a product of one or more prime numbers. A prime number is defined to be an integer greater than 1 that is only divisible by itself and 1. Proof: recall that a prime number is an integer greater than or equal to 2 that is only divisible by itself and 1. The number 1 is not considered to be prime. Let P of n be the predicate n can be expressed as a product of prime numbers. Basic step: n equal to 2. Since 2 is prime, 2 can be expressed as a product of prime numbers in a trivial way, just one factor. Thus P of 2 is true. Induction step: let n be an integer with n greater than or equal to 2. Suppose that every integer j, 2 less than or equal to j less than or equal to n, can be expressed as a product of prime numbers. The integer n plus 1 is either a prime number or it is not. Example 1. In this example, the first principle of induction would be virtually impossible to apply since the integer n is not a factor of n plus 1 when n greater than or equal to 2. That is, knowing the factors of n doesn't tell us anything about the factors of n plus 1. Case 1. If n plus 1 is a prime number, then it is a product of prime numbers in a trivial way. Case 2. If n plus 1 is not a prime number, then n plus 1 equal to a into b, where a and b are positive integers, both different n plus 1 and 1. Thus 2 less than or equal to a less than or equal to n and 2 less than or equal to b less than or equal to n. By the induction hypothesis, a and b can each be expressed as a product of prime numbers, say a equal to p1, p2, etc. pr and b equal to q1, q2, etc. qs. Since n plus 1 equal to a into b equal to p1, p2, etc. pr, q1, q2, etc. qs, n plus 1 can also be expressed as a product of prime numbers, namely the product of primes that multiply to give a times the product of primes that multiply to give b. By the second principle of mathematical induction, every n greater than or equal to 2 can be expressed as a product of prime numbers. Example 2. Prove 5n plus 5 less than or equal to n square for all integers n less than or equal to 6. Proof: let P of n be the statement 5n plus 5 less than or equal to n square. Number 1. Basis step: n equal to 6. Since 5 into 6 plus 5 equal to 35 and 62 equal to 36, this is clear, thus P of 6. 2. Induction step: assume P of n 5n plus 5 less than or equal to n square for some integer n less than or equal to 6. Use the induction hypothesis to prove 5 times of n plus 1 plus 5 less than or equal to n plus 1 whole square. First rewrite 5 times of n plus 1 plus 5 so that it uses 5n plus 5. 5 times of n plus 1 plus 5 equal to 5n plus 5 plus 5. By the induction hypothesis, we know 5n plus 5 plus 5 less than or equal to n square plus 5. Now we need to show n square plus 5 less than or equal to n plus 1 whole square equal to n square plus 2n plus 1. To see this, we note that when n less than or equal to 2, 2n plus 1 less than or equal to 2 into 2 plus 1 equal to 5. And so, this is also valid for n less than or equal to 6. Thus, when n less than or equal to 6, 5 times of n plus 1 plus 5 equal to 5n plus 5 plus 5. 5n plus 5 plus 5 less than or equal to n square plus 5. Then, n square plus 5 less than or equal to n square plus 2n plus 1. Then, n square plus 2n plus 1 equal to n plus 1 whole square, which shows 5 times of n plus 1 plus 5 less than or equal to n plus 1 into 2. By the principle of mathematical induction, it follows that 5n plus 5 less than or equal to n square for all integers n less than or equal to 6. Example 2. In example 2, the predicate P of n is 5n plus 5 less than or equal to n square, and the universe of discourse is the set of integers n greater than or equal to 6. Notice that the basis step is to prove P of 6. You might also observe that the statement P of I is false, so that we can't start the induction any sooner. In this example, we are proving an inequality instead of equality. This actually allows you more huge room, but sometimes that extra freedom can make it a bit more difficult to see what to do next. In this example, the hardest part conceptually is recognize that we need another inequality 5 less than or equal to 2n plus 1, which holds whenever n greater than or equal to 2. A good approach to showing f of n plus 1 less than or equal to g of n plus 1 is to start with f of n plus 1. Think of a way express f of n plus 1 in terms of f of n so that you can use the induction hypothesis, then find ways to get to g of n plus 1 using further equalities or inequalities that go in the right direction. In the induction step, we use the fact that if you know a less than or equal to b, then a plus 5 less than or equal to b plus 5. The induction hypothesis gives as an inequality, then we add 5 to both sides of that inequality, prove P of n plus 1. Example 3. Prove a set with n elements n less than or equal to 0 has exactly 2 power n subsets. Proof. Let P of n be the statement a set with n elements as 2n subsets. Basis step n equal to 0. The only set with 0 elements is the empty set pi, which has exactly one subset, namely pi. We also have 2 power 0 equal to 1. Therefore, a set with 0 elements has exactly 20 subsets, thus P of 0. Induction step. Let n belongs to n. Assume P of n. Every set with n elements has 2n subsets. Use the induction hypothesis to prove a set with n plus 1 elements has 2n plus 1 subsets. Suppose A is a set with n plus 1 elements, say A equal to A1, A2, etc. An plus 1. Let B be the subset A1, A2, etc. An of A. Since B has n elements, we can apply the induction hypothesis to B, which says that B has exactly 2n subsets. Each subset S of B corresponds to exactly 2 subsets of A, namely S and SU, An plus 1. But every subset of A is of one of these 2 forms, hence A has exactly twice as many subsets as B. Thus, A has exactly 2 less than or equal to 2n equal to 2n plus 1 subsets. By the principle of mathematical induction, it follows that a set with n elements has exactly 2n subsets for all n greater than or equal to 0. The greatest common divisor. The greatest common divisor of two integers a and b is the greatest integer that divides both a and b. Two integers a and b, not both 0, can have only finitely many divisors and thus can have only finitely many common divisors. In this section, we are interested in the greatest common divisor of a and b. Note that the divisors of a and that of modulus of a are the same. We denote the greatest common divisor of two integers a and b by a, b. we also define 0, 0 equal to 0. The greatest common divisor. Example, the greatest common divisor of 24 and 18 is 6. In other words, 24, 18 equal to 6. The greatest common divisor of 9 and 16 is 1. Thus, they are relatively prime. There are couples of integers, example 3 and 4, etc., whose greatest common divisor is 1. So, we call such integers relatively prime integers. There are couples of integers, example 3 and 4, etc., whose greatest common divisor is 1. So, we call such integers relatively prime integers. Note that every integer has positive and negative divisors. If a is positive divisor of m, then minus a is also a divisor of m. Therefore, by our definition of the greatest common divisor, we can see that a comma b equal to modulus of a comma modulus of b. The greatest common divisor. Theorem 1. The theorem states that if we divide two integers by their greatest common divisor, then the outcome is a couple of integers that are relatively prime. If a comma b equal to d, then a divides b, comma b divides d equal to 1. Proof. We will show that a equal to d and b equal to d have no common positive divisors other than, assume that k is positive common divisor such that k such that a divides b and k such that b divides d. As a result, there are two positive integers m and n such that a divides b equal to km and b divides d equal to kn. Thus, we get that a equal to kmd and b equal to knd. Hence, kd is a common divisor of both a and b. Also, kd greater than or equal to d. However, d is the greatest common divisor of a and b. As a result, we get that k equal to 1. The greatest common divisor. Theorem 2. The greatest common divisor of two integers does not change when we add a multiple of one of the two integers to the other. Let a, b and c be integers, then a comma b equal to a plus cb comma b. Proof. We will show that every divisor of a and b is also a divisor of a plus cb and b and vice versa. Hence, they have exactly the same divisors, so we get the greatest common divisor of a and b will also be the greatest common divisor of a plus cb and b. Let k be a common divisor of a and b by theorem 1, k such that a plus cb, and hence k is a divisor of a plus cb. Now assume that is a common divisor of a plus cb and b. Also by theorem 1, we have factorial a plus cb into cb equal to a. As a result, is a common divisor of a and b, and the result follows. The greatest common divisor. Definition. Let a1, a2, etc. an be integers, not all 0. The greatest common divisor of these integers is the largest integer that divides all the integers in a set. The greatest common divisor of a1, a2, etc. an is denoted by a1, a2, etc. an. The integers a1, a2, etc. an are said to be mutually relatively prime if a1, a2, etc. an equal to 1. Example. The integers 3, 6, 7 are mutually relatively prime since 3, 6, 7 equal to 1, although 3, 6 equal to 3. The integers a1, a2, etc. an are called pairwise prime if for each I factorial equal to j, we have ai, aj equal to 1. Example. The integers 3, 14, 25 are pairwise relatively prime. Notice also that these integers are mutually relatively prime. Notice that if a1, a2, etc. an are pairwise relatively prime, then they are mutually relatively prime. The greatest common divisor theorem 3. This theorem proves that the greatest common divisor of two integers can be written as a linear combination of the two integers. The greatest common divisor of two integers a and b, not both 0, is the least positive integer such that ma plus nb equal to d for some integers m and n. Proof. Assume without loss of generality that a and b are positive integers. Consider the set of all positive integer linear combination of a and b. The set is non-empty since a equal to 1 into a plus 0 into b and b equal to 0 into a plus 1 into b are both in the set. Thus, this set has a least element d by the well ordering principle. Thus, d equal to ma plus nb for some integers m and n. We have to prove that d divides both a and b and that it is the greatest divisor of a and b. By the division algorithm, we have a equal to dq plus r, comma 0 into r less than d. Thus, we have or equal to A minus dq equal to A minus q times of MA plus NB equal to 1 minus QM times of A minus QNB. We then have that R is a linear combination of A and B since 0 less than or equal to or less than D, and D is the least positive integer, which is a linear combination of A and B, then R equal to 0 and A equal to DQ. As a result, we conclude that if A, B equal to 1, then there exist integers m and n such that MA plus NB equal to 1. The Euclidean algorithm. A systematic method that determines the greatest common divisors of two integers. This method is called the Euclidean algorithm. If A and B are two integers and A equal to BQ plus R, where also Q and R are integers, then A, B equal to R, B, we have BQ plus R, B equal to B, R. The above lemma will lead to a more general version of it. We now present the Euclidean algorithm. In its general form, it states that the greatest common divisor of two integers is the last non-zero remainder of the successive division. The Euclidean algorithm. Let A equal to R0 and B equal to R1 be two positive integers where A greater than or equal to B. If we apply the division algorithm successively to obtain that Rj equal to Rj plus 1, Qj plus 1 plus Rj plus 2, where 0 less than or equal to Rj plus 2 less than Rj plus 1. For all j equal to 0, 1, 2, etc. n minus 2 and Rn plus 1 equal to 0, then A, B equal to Rn. By applying the division algorithm, we see that R0 equal to R1, Q1 plus R2, 0 less than or equal to R2 less than R1. R1 equal to R2 Q2 plus R3, 0 less than or equal to R3 less than R2, etc. Rn minus 2 equal to Rn minus 1, Qn minus 1 plus Rn 0 less than or equal to Rn less than Rn minus 1. Rn minus 1 equal to Rn Qn. Notice that we will have a remainder of 0 eventually, since all the remainders are integers and every remainder in the next step is less than the remainder in the previous one. We see that A, B equal to B, R2 equal to R2, R3 equal to etc. equal to Rn, 0 equal to Rn. The Euclidean algorithm. Hence 4147, 10,672 equal to 29. We now use the steps in the Euclidean algorithm to write the greatest common divisor of two integers as a linear combination of the two integers. The following example will actually determine the variables m, and the following algorithm can be described by a general form, but for the sake of simplicity of expressions, we will present an example that shows the steps for obtaining the greatest common divisor of two integers as a linear combination of the two integers. The Euclidean algorithm. Example. Express 29 as a linear combination of 4147 and 10,672. 29 equal to 551 minus 9.58 equal to 551 minus 9 into 609 minus 551.1 equal to 10.551 minus 9.609 equal to 10 into 1769 minus 609. The Euclidean algorithm. Example 2. Euclidean algorithm to find the greatest common divisor of two positive integers has number of divisions less than or equal 5 times the number of decimal digits in the minimum of the two integers. Let A and B be two positive integers where A greater than B. Applying the Euclidean algorithm to find the greatest common divisor of two integers with A equal to R0 and B equal to R1, we get R0 equal to R1 Q1 plus R2 less than or equal to R2 less than R1. R1 equal to R2 Q2 plus R3 less than or equal to R3 less than R2, etc. Then Rn minus 2 equal to Rn minus 1 Qn minus 1 plus Rn less than or equal to Rn less than Rn minus 1. Then Rn minus 1 equal to Rn Qn. The Euclidean algorithm, example 2. Notice that each of the quotients q1, q2, etc. qn minus 1 are all greater than 1 and q1 greater than or equal to 2. This is because Rn less than Rn minus 1. Thus we have Rn greater than or equal to 1 equal to F2, Rn minus 1 greater than or equal to 2Rn, to F2 equal to F3. Then Rn minus 2 greater than or equal to Rn minus 1 plus Rn greater than or equal to F3 plus F2 equal to F4. Rn minus 3 greater than or equal to Rn minus 2 plus Rn minus 1 greater than or equal to F4 plus F3 equal to F5, etc. R2 greater than or equal to R3 plus R4 greater than or equal to Fn minus 1 plus Fn minus 2 equal to Fn. B equal to R1 greater than or equal to R2 plus R3 greater than or equal to Fn plus Fn minus 1 equal to Fn plus 1. Thus notice that B Fn plus 1. We have Fn plus 1 greater than or equal to n minus 1 for n greater than 2. As a result, we have B greater than or equal to n minus 1. Equivalence relation. An equivalence relation on a set S is a relation on S which is reflexive, symmetric, transitive. In general, an equivalence relation results when we wish to identify two elements of a set that share a common attribute. The definition is motivated by observing that any process of identification must behave somewhat like the equality relation, and the equality relation satisfies the reflexive x equal to x for all x, symmetric x equal to y implies y equal to x, and transitive x equal to y and y equal to z and implies x equal to z properties. Example, let R be the relation on the set R, real numbers defined by x related to y, if and only if x minus y is an integer. Prove that R is an equivalence relation on R. Proof. Reflexive. Suppose x belongs to R, then x minus x equal to 0, which is an integer, thus x related to x. Symmetric. Suppose x comma y belongs to R and x related to y, then x minus y is an integer since y minus x equal to minus of x minus y. Y minus x is also an integer, thus y related to x. Suppose x comma y belongs to R, x related to y and y related to z, then x minus y and y minus z are integers. Thus the sum x minus y plus y minus z equal to x minus z is also an integer, and so x related to z. Thus R is an equivalence relation on R. Example, let R be the relation on the set of real numbers R. In example, prove that if x related to x dash and y related to y dash, then x plus y related to x dash plus y dash. Proof. Suppose x related to x dash and y related to y dash. In order to show that x plus y related to x dash plus y dash, we must show that x plus y minus x dash plus y dash is an integer. Since x plus y minus x dash plus y dash equal to x minus x dash plus y minus y dash, and since each of x minus x naught and y minus y naught is an integer, by definition of R, x minus x dash plus y minus y dash is an integer, thus x plus y related to x dash plus y dash. Equivalence classes. Given an equivalence relation or on a set S, we define the equivalence class containing an element x of S by x equal to y such that x comma y are equal to y such that x related to y. Let R be an equivalence relation on A. Let A belongs to A. The set A equal to x such that A related to x is called the equivalence class of A. The element in the bracket in the above notation is called the representative of the equivalence class. Let S equal to 1, 2, 3 and R equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. Then 1 equal to 1, 2, 2 equal to 1, 2, 3, then equal to 3. Let S equal to R and R equal to x comma y such that x square equal to y square, then 0 equal to 0, 1 equal to 1 comma minus 1, 1 by 4 equal to 1 by 4 comma minus 1 by 4, x equal to x comma minus x. Equivalence theorem. Let R be an equivalence relation on a set A, then the following are equivalent. Number 1, A related to B. Number 2, A equal to B. Number 3, A intersection B not equal to 0. Proof. 1 implies 2. Suppose A comma B belongs to A and A related to B, we must show that A equal to B. Suppose X belongs to A, then by definition of A related to X since R is symmetric, and A related to B related to A since R is transitive, and we have both B related to A and A related to X. B related to X, thus X belongs to B. Suppose X to B, then B related to X since A related to B and R is transitive. A related to X, thus X belongs to A. We have now shown that X to A if and only if X to B, thus A equal to B. 2 implies 3. Suppose A comma B belongs to A and A equal to B, then A intersection B equal to A since R is reflective, A related to A, that is a 2A. Thus A equal to A intersection B, 6 not equal to 0. 3 implies 1. Suppose A intersection B, 6 not equal to 0, then there is an X to A intersection B. By definition, A related to X and B related to X since R is symmetric, X related to B since R is transitive, and both A related to X and X related to B, A related to B. Equivalence theorem explanation. Let R be an equivalence relation on a set A, then the following are equivalent. Number 1, A related to B. Number 2, A equal to B. Number 3, A intersection B not equal to 0. The purpose of any identification process is to break a set up into subsets consisting of mutually identified elements. An equivalence relation on a set A does precisely this. It decomposes A into special subsets called equivalence classes. Looking back at the example given, we see the following equivalence classes. 0 equal to Z, the set of integers. 1 by 2 equal to M by 2, such that M is an odd integer. Pi equal to pi plus n, such that n is an integer, equal to pi plus n for any integer n. These ideas are summed up in theorem when we say several statements such as P1, P2 and P3 are equivalent. We mean P1 if and only if P2, if and only if P3 is true. Notice that in order to prove that the statements are mutually equivalent, it is sufficient to prove a circle of implications such as P1 factorial, P2 implies P3 implies P1. This is how we set up the proof of theorem. Partition. A collection S of non-empty subsets of a set A is a partition of A if number 1, S intersection S dash equal to pi, if S and S dash are in S and S not equal to S dash. Number 2, A equal to union S such that S belongs to S. If S is a set with an equivalence relation R, then it is easy to see that the equivalence classes of R form a partition of the set S, and more interesting is the fact that the converse of this statement is true. Partition theorem. The equivalence class of an equivalence relation on A form a partition of A. Conversely, given a partition on A, there is an equivalence relation with equivalence classes that are exactly the partition given. The definition along with theorem describes formally the properties of an equivalence relation that motivates the definition. Such decomposition is called a partition. For example, if we wish to identify two integers, if they are either both even or both odd, then we end up with the partition of the integers into two sets, the set of even integers and the set of odd integers. The converse of the theorem allows us to create or define an equivalence relation by merely partitioning a set into mutually exclusive subsets. The common attribute then might just be that elements belong to the same subset in the partition. Partition theorem 2. If R is an equivalence relation on a set A, the set of equivalence classes of R is denoted by A by R. Suppose R is an equivalence relation on A and S is the set of equivalence classes of R. If S is an equivalence class, then S equal to A for some A belongs to A, hence S is non-empty. Since A related to A by the reflexive property, or by the partition theorem 1, if S equal to A, S not equal to B, or an S, then A equal to B, if and only if A intersection B not equal to pi. Since this is a biconditional, this statement is equivalent to A not equal to B, if and only if A intersection B equal to pi, since each equivalence class is contained in A. S, S such that S belongs to S is a subset of A. But as we just saw, every element in A is in the equivalence class. It represents A union S, S such that S belongs to S. This shows S such that S belongs to S equal to A. Intersection of equivalence relations. If R1 and R2 are equivalence relations on a set A, then R1 intersection R2 is an equivalence relation on A. To prove this, it suffices to show the intersection of reflexive relations is reflexive, symmetric relations is symmetric, and transitive relations is transitive. Intersection of equivalence relations. Example. Let M be a positive integer. The relation A identically equal to B modulus of M is an equivalence relation on the set of integers. Proof. Reflexive. If A is an integer, then A minus A equal to 0 into M, then A identically equal to A modulus of M. Symmetric. If A identically equal to B modulus of M, then A minus B equal to K into M for some integer K. Thus B minus A equal to minus K into M is also divisible by M, and so B identically equal to A modulus of M. Transitive. Suppose A identically equal to B modulus of M and B identically equal to C modulus of M, then A minus B equal to K into M and B minus C equal to 1 into M for some integers K and 1. Then A minus C equal to A minus B plus B minus C equal to K into M plus 1 into M equal to K plus 1 into M is also divisible by M, that is A identically equal to C modulus of M. Infimum. If A belongs to A is the lower bound for B. If for every B belongs to B, A related to B, also A is called a greatest lower bound or infimum for B if number 1. A is the lower bound for B, and 2. X related to A for every lower bound X for B. In the example ASCII diagram, consider B equal to 2, 3. Both 6 and 12 are upper bounds of this subset, and 6 is the supremum of B. The only lower bound of B is 1 and infimum of B equal to 1. Now let B equal to 4, 6. Supremum of B equal to 12 and infimum of B equal to 2. Consider the set C equal to 2, 3, 5. There is no upper bound for C, and 1 is a lower bound and also infimum of C. Fibonacci numbers. Fibonacci numbers, the mathematics associated with them is interesting because surprisingly they are intimately related with the complexity analysis of the Euclidean algorithm. Here are the first 16 Fibonacci numbers: 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 377, 610. The convention is to start numbering at 0, so that we have listed the 0th, the 1st, etc. and the 15th Fibonacci number. We denote the nth Fibonacci number by Fn for each non-negative integer n. There is an easy method for obtaining the Fibonacci numbers. First, f equal to 0, f1 equal to 1, then for all n greater than or equal to 2, fn equal to fn minus 1 plus fn minus 2. Fibonacci numbers and mathematical induction. Since the nth Fibonacci number is defined in terms of smaller Fibonacci numbers, it is natural to try to build proofs about these numbers using induction. However, the nth Fibonacci number is not defined solely in terms of its immediate predecessor, but rather in terms of two predecessors. Consequently, we need a strengthening in our induction machine. Algorithm. Induction. Step 1. Verify the base case. Step 2. Assume that pk is true for an arbitrary value of k. Step 3. Verify that pk plus 1 is true using the assumption that pk is true. Fibonacci numbers and complete induction. Sometimes the truth of pk plus 1 depends on the truth of more than one of the preceding pj's, or depends on the truth of pj where j less than k. there is still hope for the method of induction if we use the following principle, which is known as complete induction. Suppose that Pn is a proposition that depends upon the positive integer n, then Pn is true for all n greater than or equal to n, where n is some fixed integer, provided that Pn is true, and if Pn, Pn plus 1, etc. and Pn are all true, then so is Pn plus 1. There are two changes here. First, we have introduced an unspecified constant n. In the original version of induction, we always mention the base case P1, although we admitted that the base case might start off at P0. Fibonacci numbers and complete induction. The second difference between induction and complete induction is in the inductive hypothesis. In the second version, we assume that Pn, Pn plus 1, etc. and Pn are all true. Since we assume more, it should be easier to use this form. The algorithm version of complete induction. Algorithm induction. Step 1. The base cases. Verify that Pn, Pn plus 1, etc. Pn plus j are valid for some constants n and j depending upon the problem. Step 2. The inductive hypothesis. Assume that Pn, Pn plus 1, etc. and Pn are all true for an arbitrary value of k. Step 3. The inductive step. Verify that Pn plus 1 is true. Using the inductive hypothesis, there is one more change introduced in algorithm, namely the constant j in step 1. At times, we shall need to check more than one base case. Depending on the proof, we construct to show that pk plus 1 is true. The value of j depends upon the number of pk, pk plus 1, etc. pk that we refer back to in our verification of pk plus 1. Fibonacci numbers theorem. Every integer n greater than 1 has a prime divisor. The statement gives the starting point of the proposition n equal to 2. This statement is true for n equal to 2 since 2 is a prime number and divides itself. Similarly, the statement is valid for n equal to 3 since 3 is a prime. We check that it is also true. The inductive hypothesis tells us to assume the truth of the statement for n equal to 2, 3, etc. k. For some arbitrary value of k, to accomplish the inductive step, we must prove the result that the integer k plus 1 has a prime divisor. Now either k plus 1 is a prime or it isn't. If k plus 1 is a prime, then it has itself as a prime divisor. If k plus 1 is not a prime, then k plus 1 equal to bc, where b and c satisfy 1 less than b less than k plus 1 and 1 less than c less than k plus 1. Consider b. By the inductive hypothesis, since 1 less than b less than k plus 1, we may assume that b has a prime divisor, say p, then k plus 1. Fibonacci numbers. Theorem continued. Every integer n greater than 1 has a prime divisor. K plus 1 divided by p equal to b by c equal to b by p into c. We see that k plus 1 by p is an integer. Since it is expressed as the product of two integers, this means that p is a divisor of k plus 1, and so k plus 1 has a prime divisor, namely p into q. Note that we could not have used the standard form of induction in this problem because the truth of the assertion pk plus 1 depends not on the truth of pk but on the truth of pb, where b is less than k. Since our proof depends upon only one earlier case, p follows with 1 less than b less than k plus 1. Our base case needed only one value, namely n equal to 2 and j equal to 0. Although to get a feel for the problem, we checked 3 base cases. We now use complete induction to establish some facts about the Fibonacci numbers. Fibonacci numbers. Rabbit out of the hat tricks. Find an integer n such that fn greater than 3 by 2 whole power n. Prove by induction that f greater than 3 by 2 whole power n for all n greater than n, which is a rabbit out of the hat tricks with the Fibonacci numbers. A pair of rabbits requires 1 month to mature to the age when it can reproduce. Suppose that the rabbits then mate and produce another pair in every subsequent month, and that the pair of offspring is always conveniently one male and one female, who then form a new breeding pair. If in the first month we have one pair of rabbits, how many pair do we have at the beginning of the nth month? For simplicity, we assume no death or laws of fertility. We call the resulting number R. At the beginning of the first month, we have one pair, so R1 equal to 1. At the beginning of the second month, we still have one pair, but during the second month, they produce a pair of bunnies. This R2 equal to 1 and R3 equal to 2. During the third month, the original pair produces another pair of bunnies, but the new pair of bunnies doesn't reproduce yet. So R4 equal to 3, then R5 equal to 5. Fibonacci numbers. Rabbit out of the hat tricks. We might as well argue the general case, that is, let's determine R in terms of previous values of R. At the beginning of the nth month, we have all the rabbit pairs that we had at the beginning of the n-1st month. R minus follows plus some new bunny pairs. The number of new bunny pairs is the number of rabbit pairs that are at least 1 month old. The rabbit pairs that are this old are precisely those that were around in the n-2 month. Rn-2. In symbols, then Rn equal to Rn-1 plus Rn-2. Now we see that this R are exactly the same as the Fibonacci numbers and that R equal to F for all positive n. Fibonacci numbers arise in other natural settings. For example, the spacing of leaves on some plants and some arrangements of flower petals and seeds are closely related to the Fibonacci numbers. Mollusk shells spiral in curves derived from Fibonacci numbers. Ratios of successive Fibonacci numbers like 5 by 3, 3 by 8 and are considered aesthetically pleasing. The squares in figure 4.1 each have sides equal to a Fibonacci number. They combine to make rectangles with sides in ratios of 34 to 21, 21 to 13, 13 to 8, 8 to 5, 5 to 3, 3 to 2 and 2 to 1. In fact, two large values of n, fn by fn minus 1 gets arbitrarily close to a constant. Fibonacci squares. The Fibonacci numbers are even thought to be useful in predicting highs and lows on the stock market. These numbers have so many interesting and varied properties that there is a mathematics research journal, the Fibonacci Quarterly, dedicated to results about Fibonacci numbers. The defining property is useful for proving results about Fibonacci numbers by induction, but one thing seems missing from our knowledge. Is there a formula for Fn or to calculate, say, F17? Must we determine all the smaller Fibonacci numbers S and maybe no, respectively? We shall write down a formula for F, but we stress that in most situations the inductive definition that Fn equal to Fn minus 1 plus Fn minus 2 is the most helpful fact to know. Fibonacci numbers contradictions. To calculate F by adding as shown above appears to require that we store all of F0, F1, etc. Fn minus 1. Is it possible to calculate F by addition without storing all previous values in n different memory locations? What is the minimum number of memory locations that you need to calculate F in this way? The second way we know how to calculate Fn is using the formula in previous stated theorem. This requires two exponentiations, one division and one subtraction, as well as an approximation of the square root of 5. There are a variety of additional methods known for calculating F, including an addition method that is analogous to the FAST-EXP algorithm, that is, one that does not require the determination of all intermediate Fibonacci numbers. Conclusion. In this chapter, the user have covered the following aspects of number theory: greatest common divisors, Euclidean algorithms, Fibonacci numbers, complexity of Euclidean algorithms, congruences and equivalence relations, public key encryption schemes, dividends.